Hello everyone, and welcome to another ICTS virtual string seminar. We are happy to have Jaume Gomis from Perimeter Institute with us today, and he's going to tell us about global anomalies on the Hilbert space. Over to you, Gomis.
Okay, well, thank you very much for the invitation. I know for many of you this is a very strange time to give a seminar. I mean, to hear a seminar Friday night, but I don't know, that's how it was scheduled. Today I'm going to describe some work that I've done with colleagues at Perimeter, Diego Del Mastro and Matthew Yu, which are my students, even though I guess the last work I won't really have much time to say much about it, and with Davide Gaiotto. And the subject of the talk is about global anomalies. So this is a subject for which in the last few years there has been, I think it's fair to say, there's been a tremendous amount of progress. And that progress has led to kind of answering long-standing questions in the field. And it also it's a subject that has kind of had insights coming from several areas, including condensed matter, quantum information, high energy physics, and mathematics. And kind of this progress has led to long-standing answers in those fields. So in this talk, I will kind of just give you, I will present kind of a way to detect global anomalies. Well, I'll define what I mean by that. Global anomalies in a rather elementary way that does not rely on the usual detection mechanisms like computing A-time variance and more complicated things of that sort, but a very elementary mechanism to detect at least a certain class of global anomalies by studying the Hilbert space of the theory. Then another thing I want to kind of outline is how, one of the progresses in the last years has been to give a mathematical classification of anomalies in terms of certain generalized cohomology theory. And essentially, one of the things that I will do is to show how the different ingredients that enter in the classification of global anomalies leave different imprints, distinguished imprints, as an anomaly in the way the symmetries are realized in the Hilbert space. So each ingredient in the mathematical construction has a counterpart in the physical implementation of how the anomaly is detected. And then I'll provide some simple examples so that it doesn't sound like abstract nonsense, and you will see that it's very elementary to detect these anomalies. And as an interesting application, we will discuss how systems, including strongly coupled gauge theories that have a particular type of global anomaly, how these anomalies imply a non-trivial result about the spectrum of the theory. Particularly, it will tell us that when those theories have a particular type of anomaly that I will describe in detail, those theories have a supersymmetric spectrum. So there's a exact Bose-Fermi degeneracy in the spectrum, even though the theory that you started with had no supersymmetry to be found anywhere. And this will be an example in which supersymmetry is a consequence of an anomaly, but not of supersymmetry. Okay. So I have a lot of many more slides that I will have time for. The talk is 1 hour, correct?
Yes.
Yeah. So I mean, I will pick and choose, and feel free to stop me anytime, so I don't feel like myself. That's how things go these days. Okay, so let me start with just an introduction. Okay. So let's start with the preamble of anomalies to symmetries. Okay? So as we all know, symmetries are a powerful organizing principle in physics, and symmetries come in all different types. And as a function of time, we learned that actually there are more symmetries than we thought were available before. And whenever you have more symmetries, you have more constraints, and you can learn more things about dynamics. So from the old days, we know that they are roughly speaking discrete and continuous symmetries, and you can roughly classify them as a space-time and internal, even though the two types of symmetries can mix in a non-trivial way in examples. And in more recent times, it has realized that so these are the symmetries that you find in textbooks, in quantum field theory textbooks. That there are new types of symmetries that have come to the forefront or kind of become more manifest in the last few years, like higher form symmetries. which, unlike the ones that I've discussed, the ones that I've listed above here, are essentially symmetries that act on the local operators of the theory. You can have symmetries that act on higher dimensional operators on the theory, like line operators. They also can have lead to constraints in the dynamics. It can also happen that the usual zero form or conventional symmetries mixed with these guys to generate mathematical structures called two groups, three group symmetries. And these have only become like really more understood in very recent times. Also, if you're able to, if you're willing to relax a little bit what your notion of what a symmetry is, there are other objects that have been studied in recent times that play a very similar role to conventional anomalies and lead to powerful constraints on its dynamics and can also have anomalies, which that are usually referred to as non-invertible symmetries. So we see that there are many types of symmetries. In recent times, we've discovered new ones, and they've been put to very good use. Okay. So symmetries are great, but what do they really do for us? I mean, symmetries, in a sense, all that they do is parameterize the most general possible answer to the dynamics of a physical system. Okay? So in particular, it implies selection rules and constraints and related observables via word identities. But it really doesn't tell you anything about the answer. It just tells you the most general parameterization of what the answer will look like. But it doesn't tell you at all what the answer is. You need some other input to tell you what the actual answer is. Symmetries just tell you the optimal way of parameterizing the answer. Okay, so now that but of course you want to simplify things.
Jaume, I have a question. This is Mithat, by the way.
Oh, hi, Aria.
I have a question. Can all of these symmetries that you listed be used to detect anomalies?
Can what?
Can all of these symmetries you listed, can they be used to detect anomalies?
You mean in the method that I'm describing, or more generally?
More generally, for more specifically, I am asking about non-invertible symmetry. Can it be used to detect some interesting mixed anomaly?
Well, so I think this is best understood in 1 + 1 dimensions. So in 1 + 1 dimensions, the generalization of, okay, I'll make it a small, this is a very technical remark that maybe it's too advanced, but let me just say it. So two-dimensional quantum field theory is the right notion of a symmetry is that of a fusion category. So where symmetries, the generalization of a symmetry is implemented by topological lines that are not necessarily invertible. And that fusion category, when you try to gauge it, may have Tooth anomalies, yes. So they definitely, fusion categories can have Tooth anomalies, and therefore non-invertible symmetries can have Tooth anomalies.
Okay, then, yeah, this may have very interesting implications. Okay, thank you.
Absolutely,
yeah.
Yes.
Yeah.
And please feel free to stop me. Okay, so now that we have parameterized the dynamics using the symmetries, now the hard problem, the hard task really starts, which is to solve the dynamics of the system. But this is, of course, extremely hard. And if your system has a weak coupling, coupling parameter, then you can try to solve the dynamics doing perturbation theory. But for strongly coupled systems, there really is no systematic or universal tools to discern what the dynamics actually is. An important exception to this is Tooth anomalies, which do not tell us what the answer is, but informs the dynamics. And essentially, Tooth anomalies tells you what the answer cannot be in the space of all possible answers, and gives you possible candidates of what the answer can be. So I'll describe this in more detail, but essentially, a Tooth anomaly describes a violation of a symmetry when the system is coupled to background not dynamical gauge fields for the symmetries. So in this talk, whenever I talk about an anomaly or a Tooth anomaly, it's always an anomaly for a global symmetry where I have coupled my system to background gauge fields that are fixed and external. They're not path integrated over them. Okay? So the reason that anomalies are very useful is that anomaly, as I will come back to later, is that anomalies that miss a topological classification. Actually, recently, a very sophisticated classification, but topological nevertheless, which makes, and since they're quantized, they're being topological, they are invariant under symmetric deformations, including scale transformations. So it is one of the very few things that we can know with certainty. If you can detect them at one energy scale, say typically at very short distances, we know that it will have to be there at any energy scale, in particular in the deep infrared. So it informs you directly of what the infrared of your system will have to obey. And that can rule out and can and has ruled out potential scenarios for infrared dynamics of strongly propagated theories. Okay. One reason that Tufts anomalies are observed, that's of course a very powerful tool to kind of constrain the possible outcomes of the dynamics of the system. But I think that's important is that Tufts anomalies give rise to powerful non-perturbative theorems. It tells you immediately that if the anomaly, if you have a Tufts anomaly and it's non-vanishing, then the ground state of your system cannot be trivial because a trivial system has an anomaly. So it immediately tells you that your system has something non-trivial in the infrared. It's just not gapped and trivial. And as I said, the existence of Tufts anomalies leads to constraints on the candidate dynamics that you have to satisfy. But I want to repeat that it doesn't tell you what the answer is, but it tells you what the answer cannot be. But at least you can reduce the space of possibilities. All right, so maybe this was a little bit abstract. Let me give you a couple of examples of the power of Tufts anomalies to learn something about the infrared of interesting systems. So I'll start with an example that's very, very simple. So consider the famous spin-and-a-half Heisenberg spin chain on a circle. So you have a collection of spins on a circle. And each side is a spin-and-a-half particle, and they interact with the Heisenberg Hamiltonian. Now, the Heisenberg Hamiltonian has an SU2 symmetry, but now I want to do the following. I want to essentially write down the most general interaction, in particular breaking the SU2 symmetry, but I only allow interactions that involve an even number of spins. So these are interactions that in particular, they're nearest neighbor close range interactions, but involve an even number of spins. Okay. Now, if you try to imagine you want to compute the Hamiltonian in mathematics, this will be a huge mess. You know, you have many couplings, and there doesn't seem to be much a priori that you could be able to say about the spectrum of this theory. But actually, there is because since the terms here allow quadratic in the spin, this system has a time reversal symmetry. T squared equals 1, where you will remember from your quantum mechanics courses that under time reversal, spins get changed, get reversed. So something like this. So therefore, if I have an even number, if all interactions involve an even number of spins, and then this is more, this is huge, then the system is time reversal symmetric. Okay. And we know what implements this time reversal transformation is just the Pauli matrix sigma 2. Okay. Now the point is that this system has a Tufts anomaly if the number of sides on the circle, the number of spins in the circle is odd. Okay. Essentially because if L is odd, essentially the Z2C, the time reversal symmetry is realized projectively in the Hilbert space. So while in all operators T squared equals -1, if L is odd, T squared equals -1 on the Hilbert space. So that means that the symmetry is realized projectively on the Hilbert space of this spin chain. Okay. And this is tantamount in quantum mechanics to saying that the system has a time reversal anomaly for L odd. Okay. The fact that you have an anomaly implies immediately, and this is seen more clearly from the point of view that the symmetry is realized projectively. Since there are no one-dimensional projective representations, it immediately tells you that the ground state is doubly degenerate. Okay. In fact, all states are doubly degenerate. Okay. So we see here in a very simple example in which the existence of a time reversal symmetry within a Tufts anomaly tells you something non-trivial about the spectrum of the theory, namely that it's doubly degenerate. Every state is doubly degenerate due to the anomaly for the time reversal symmetry. Good. A more recent and a more interesting example is trying to answer the following question. So these are the kind of long-standing questions that particle physicists aim to answer, which is to understand infrared dynamics of QCD theories in various dimensions. So let's consider a simple theory that you would have thought that people know the answer to this for a long time. Let's consider SUN, Yang-Mills theory in 2+1 dimensions with a quark in the adjoint representation. Now, something that you can say about this theory immediately is that this theory has a time reversal symmetry of the type t squared equals -1 to the f. This is the standard time reversal symmetry that you find in Peskin and Schroeder, so to speak, in high energy physics. Okay. And more sophisticatedly has, but not really, it has a Zn one form symmetry. That essentially this Zn is the subgroup of the center of SUN. Okay. Now, something that is less trivial to show is nevertheless, because the theory is essentially free in the deep ultraviolet, is that this theory has Tooth anomalies for these two symmetries. Okay, so this immediately tells you that the infrared of this theory cannot be trivial. This is to be okay, that doesn't matter. Yeah, so this is to be contrasted with other examples of QCD theories where are gapped and trivial in the infrared. Okay, so now another question is what does happen, just like in this example, what happens in the deep infrared of this theory? So essentially using Tooth anomalies and of course many more arguments than I don't have time to describe, you can propose that in the infrared there's a particular, the details here don't really matter, but just to say that the existence of Tooth anomalies for these symmetries predicts that in the infrared there has to be something non-trivial, and there is a very concrete proposal of some emergent gauge theory that appears in the infrared that describes the infrared dynamics of this thing. And again, an important guide for this was the existence of these Tooth anomalies. And notice that this leads to surprising behavior for the infrared dynamics of these theories, like emergent gauge fields and anions and the confinement of the quarks. Notice that here there is the confinement while all quarks, dynamical quarks, are at adjoint representation. So these are two simple examples of how the existence of Tooth anomalies can tell you something quite dramatic about the infrared of systems. All right. So now
hello, can
yes.
I ask a question?
Of course.
About your previous slide. Regarding this adjoint QCD example, so both the time reversal symmetry and the one form symmetry are anomalous. Is that
that's correct? Yes. Yeah. So I took the example that this time reversal anomaly takes values in is a Z16. So it's an integer mod 16, and the one form anomaly for the Zn one form symmetry is a Zn anomaly.
And is there a mixed anomaly also in some sense? Or?
No, there is no mixed anomaly in this case.
Okay. Okay. Thanks.
But there are many examples, like in 2 dimensions of a mixed. Well, there are many examples in many dimensions that where you have mixed anomalies between 0 form and 1 form symmetries, and they imply interesting things about the infrared dynamics. So let's describe a little bit more systematically what a Tooth anomaly is. So let me see how much I'm going so slow. Okay, no matter. So a system has a Tooth anomaly if, when we couple it to background connection for the symmetry G that you're trying to study, the non-invariance of the partition function and their background gauge transformations cannot be cancelled by a local counterterm. So this is more or less the standard definition of a Tooth of an anomaly that you would find in Peskin and Schroeder, but this is also true for discrete symmetries here. Essentially, if you make a background gauge transformation, so A is the connection that couples to the background gauge field for G, and if I make a gauge transformation, it will transform in this fashion. And if this phase cannot be cancelled by a local counterterm, if I can cancel by a local counterterm, we don't call it an anomaly because that just means that it's an effect that can be removed by a change of regularization. It's a man-made phase. It's not a physical phase. Human-made phase. Okay, so what do we know about these phases? These phases satisfy, they're not just random phases, they have to satisfy certain physical constraints. The most famous one is that for continuous symmetries, so that here is when I want to start distinguishing between continuous and discrete symmetries. For continuous symmetries, this phase alpha has to satisfy the Waelz-Zuminian consistency conditions. Essentially, just a statement that transformations concatenate properly. So the anomaly has to satisfy a certain concatenation rule, essentially some kind of associativity. Okay. So that's true for continuous symmetry. The analog of this for discrete symmetries is pentagon-like identities for discrete symmetries. So the point is that gauge fields, discrete gauge fields, so gauge fields for discrete symmetries can be represented either by a background connection or by a network of topological defects that say have trivalent junctions. And there, the statement of background gauge transformations is a statement that these networks reconnect. The associativity of the network reconnection is captured by pentagon identities, if you're familiar from two-dimensional conformal field theory. Okay. So these are certain constraints that the anomalies have to satisfy, even if you know nothing else about them. Okay. Now, one important insight that has played a very important role, especially in condensed matter physics, is that, but not only there, is that an anomaly, the actual anomaly is captured by inflow from a topological term in one dimension higher. Okay? And the physical meaning of these topological terms that it describes what condensed matter people call a symmetry protected phase in one higher dimension. So these are phases of matter that are essentially trivial on a closed manifold, but not if you put the manifold on with a boundary. Okay? And the boundary then necessarily has to be something non-trivial going on. And what's going on the boundary is precisely a system that reproduces the anomaly that you were studying. So the main message here is that you have a system in D dimensions that will have a tooth anomaly. It has a non-invariance of the partition function here. But now if you attach this D-dimensional system to the boundary of a suitable D+1 dimensional topological system, then the combined system is invariant. Okay. So there is a nice dictionary where you can shuffle things around between anomalies in D dimensions and SPT phases in D+1 dimensions. And this has been interesting in condensed matter because in particular they also have experimental examples of such SPT phases. Okay, good. So this was the abstract definition. So one thing to say here is that this kind of language of anomalies clearly has a cohomological flavor because you're looking at transformations modulo exact things. Okay. So the general question is how do we classify? What is a mathematical classification? The mathematical framework to classify anomalies in general? So as I've been arguing, these anomalies are classified by quantized topological classes, and this was of course known. For a very long time for fermionic systems for continuous symmetries. That's essentially what you find in field theory textbooks. But the point is that these anomalies can happen both in bosonic and fermionic systems, but for continuous, but also discrete symmetries. And that has been kind of where I think a lot of the progress has happened. Not much new has been able to say about the usual anomalies. Those were there and already understood. Okay? The thing that's good about them is precisely because they're quantized, that they're invariant, they're robust, and they're G-symmetric deformations. And in particular, they're insensitive to adding massive degrees of freedom that do not spoil the symmetry. So in a sense, the existence of these anomalies allow you to probe certain homotopies in the space of quantum field theories, because you can add arbitrary massive deformations, Yukawa couplings, whatever you want, and the anomaly will remain invariant under such deformation in the space of quantum field theories. Since they're robust under G-symmetric deformations, in particular, they imply that they are renormalization group invariants, so that if you have an anomaly in the ultraviolet, it will have to be reproduced in the deep infrared, where typically you don't know what you're talking about because the system is non-perturbative. And as I said, this allows us to inform us about the strong coupling dynamics of systems that have tooth anomalies. Okay. So now let me tell you a little bit about the classification of the mathematical classification of tooth anomalies, starting with the classification of anomalies for bosonic systems. I'll use a particular language that may sound weird, but it's really the right framework to think about symmetries and anomalies in bosonic and fermionic systems later. So if you have the symmetry data of a bosonic system is given by the following pair: G, which is a group, and then this omega-1 is a class that essentially is a map from G to Z2. That's what this fancy thing means. It's a map from G to Z2 that essentially tells you what Wigner once told us to do. Any symmetry is either unitary or anti-unitary. And essentially this omega-1 tells you whether that particular group element is unitary or anti-unitary. So that the classification of the symmetry is given by these two elements, G and a class in H1. For example, if we take the group to be Z2, then there are a Z2 worth of types of symmetries. And if the class is trivial, then you get the standard unitary Z2 symmetry. While if the class is non-trivial, you get, so now the generator is antilinear, anti-unitary, and you get the time reversal symmetry. Remember that antilinear operations act by complex conjugation, okay, an antilinear map. Good. So after lots of work, it has settled that the classification of bosonic anomalies bosonic anomalies are classified by a particular twisted cobordism group. I will not describe in detail what this is, but it's some generalized cohomology theory that whose input data is precisely the symmetry, the group G and the class omega-1. Okay, and it's important that anomalies in the dimensions are classified by the cobordism group in D+1 dimension. So in fact, this really is a classification of SPT phases in D+1 dimension. So now let's say a few things about this. So if the dimension is small enough, if the space-time dimension is less or equal than 2, then this cobordism group reduces to a standard group cohomology. Okay? And this extends the classic result that anomalies in quantum mechanics, namely in D=1, are classified by H2 of GU1, which is the way you classify projective representations of group G. Okay. So this object is a natural generalization of group cohomology that extends the notion of anomalies in higher dimensions. Now, how do you compute this beast? So these are rather formidable, but and I will describe this in a bit more detail when we come to the fermionic systems. But essentially, this can be computable from a particular spectral sequence that combines this highest group cohomology degree with cohomology degrees of lower degrees. Okay, and then essentially you have maps between these cohomology groups, and this defines a certain extension problem. And this extension tells you what the classification of what this guy is, which classifies anomalies in D dimensions. Okay. And when we come to the fermionic system, we will see how these different cohomology groups of lower degrees, which we call cohomology layers, how they leave a particular imprint in the Hilbert space of your system when we get there. Okay. So now, what about fermionic systems? This will be the main thing that I will care about in this talk. So the first thing to say about fermionic systems is that these are systems that depend on the choice of a spin structure in your manifold, like, for example, a fermion. Okay. Now, let me tell you some things that are that come attached to the hip with a fermionic system. They are endowed with an unbreakable Z2 symmetry that's generated by fermion parity. Okay. And this symmetry gives the Hilbert space a particular grading. Essentially tells you the Hilbert space is a graded Hilbert space, which contains a bosonic factor and a fermionic factor. Okay? Now, classically, any symmetry G preserves fermion parity. Okay? So in the classical theory, G commutes with -1 to the F. Okay? So any symmetry that acts unitarily on or alternately in the Hilbert space is a Grassmann even, essentially. Okay? Good. Remember this because this will become important later when we discuss anomalies, where this will stop to be true in systems that have a particular type of anomaly. Okay? And this will have very strong consequences for the dynamics of the system. Now, so what are we going to say about the classification of symmetries in a fermionic system? So now in a fermionic system, to specify the
Hello?
Yes.
Yeah, sorry, question. So, so this is supposed to be a definition of a fermionic system. That is, if I have any theory which depends on the choice of a spin structure, then I should call it fermionic system.
Yes, that's essentially good.
Like even if it is written in terms of fields which are not fermionic, I should.
Yes. If it depends on the spin structure, not if if it depends on the spin structure, then it's the Fermionic system.
Okay. Okay.
That's the official definition. Yes. Is that clear?
Are there systems which are written in terms of fermionic fields, but somehow they have some additional gauge invariance or something which doesn't satisfy this property, and they're not fermionic?
There are systems that at first would look fermionic, but they're not. So a very simple example would be take a U1 gauge theory with the fermion, the Dirac fermion.
Okay.
Minus 1 to the F is part of the gauge group, because the gauge group it includes the element that maps psi to minus psi. So actually, this system, you sum over all possible spin structures. And if you sum over all possible spin structures, it means that the system is bosonic. It's like doing bosonization. So even though naively it looks like there's a fundamental fermionic field in the system, the actual system does not depend on the spin structure. Another way of saying it is that if you write down all local gauge invariant operators in your system, they're all bosonic.
Right.
Right.
Okay. Thanks.
Yeah. So let's discuss the symmetry data of a fermionic system. So now it's a bit richer than the bosonic system. So we still have some group G, W1, that again will tell us what the Wigner wants us to tell him, which is whether a particular group element is unitary or anti-unitary. But now there is a certain other data we have to specify. This W2, which is a class, is this particular class. And this follows from the fact that we already said that minus 1 to the F is central. And this class omega 2 precisely tells you what the central extension is. Okay? So another way of saying this, the total symmetry of the system is on fermionic is GF, and GF is a Z2 central extension of G, okay? Or vice versa, you can write it in this way. So in a fermionic system, we have to specify the unitary and anti-unitary of the elements, and also a particular central extension. For example, if you take the example of T squared equals minus 1 to the F, which is the usual time reversal symmetry that we find in particle physics, then this corresponds to the reduced, to this group G being Z2, and the two classes, omega 1 and omega 2, being non-trivial. So omega 1 tells you that T is antilinear, and that the fact that omega 2 is 1 and not 0, which is non-trivial, tells you that minus 1 to the F, which is the generator of Z2F, is entangled non-trivially with G. So that in fact, T squared equals minus 1 to the F. Okay. So this would be a particular example of how this data gives rise to the symmetry groups in a spin system, fermionic system. Now, fermionic anomalies are classified by twisted cobordism groups. Okay. So again, I will notice in one dimension higher. And again, I will not go into a lot of details of what the official definition of this is, because it will not be terribly important for what I'll say later. But there is this rather precise object that classifies what the anomalies are. Now, it turns out that again, this group can be computable from a spectral sequence. The technical term is called a Trier-Hilbert group spectral sequence. And the way you do it is by writing down a collection of cohomology groups with maps between them, and this defines a series of finite groups, and then the extension, a certain extension problem, determines what the anomaly is. Let me mention what the various layers that cohomologies that enter in the computation of these cobordism groups. Well, before there is a top layer that is just the naive thing that you would have written down if you didn't know any better. And that would be the group cohomology in D+1 dimensions. This is what would classify naively bosonic systems, bosonic SPT systems in D+1 dimensions. But then you see that there are cohomology groups at lower degree with different coefficients. And so notice here that the coefficients of the cohomology are U1, and here are G2, and Z. This will have a physical interpretation in a few minutes soon. So you see that there are certain ingredients that enter in the classification of anomalies that involve group cohomology at various degrees. And we will see that this has a nice counterpart in the physics in a moment. And of course, there are all these cohomology degrees, and there are non-trivial differences that connect these various classes. There are certain maps between these various cohomologies that one has to study. Okay. So now let me give you just an example of what the output of doing this analysis is for various interesting symmetries that you can have. So imagine you want to study time reversal symmetry in a fermionic system, Z2 symmetry. So it will be time reversal symmetry equals 1. So if you were a bosonic person, you would say that the anomaly is given by H2 of Z2 with values in U1, and that is a Z2. But notice that how the actual answer is Z8, and that means that contributions from lower layers concatenate the Z2 to give you a larger classification of Z8. The same thing happens here in 1+1 dimensions. If you look at Z2 unitary symmetry in 1+1 dimensions, the naive answer would be that it's labeled by H3 of Z2 with values in U1, which is a Z2. But again, contributions from layers of lower degree compile the anomaly into a Z8. And likewise, with the time reversal symmetry, this is the symmetry that people, the condenser that people call for topological superconductors. Notice that you have a large group of anomalies, which is Z16, again, that arrives from all the layers contributing kind of coherently to give you a large anomaly group. Okay. Good. Now, each layer has what I want to discuss now briefly is that each layer has a physical interpretation. I'm going super slow, but anyway. Let me say very briefly. So each layer has a physical interpretation. Essentially, for each SPT in D+1 dimensions has for the general statement, any system that has a global symmetry, associated to that, continuous or discrete, there is an associated domain, a topological domain wall that implements that symmetry. That's just a statement that, that if you take that domain wall and you encircle the operator, it acts on it. Okay? Now you can consider your SPT phase with a collection, with a domain wall that implements the symmetry, but these domain walls can join and split. They can form certain junctions. And these junctions can intersect at various codimensions. Okay? So one way to think about this generalized homology theory is that at each intersection of various codimensions, you can enrich the intersection with an SPT, a fermionic SPT, with no symmetries. By that I mean is the SPTs with the system that only has fermion parity, no other symmetries. And those have been completely classified. So in 0+1 dimensions, SPTs with no symmetries, there are Z2, a Z2, and a Z classification. Notice that this will be associated precisely with the coefficients here, Z2 times Z2 times Z. And they have different names that we don't really have time to discuss right now. Okay? But the idea that you should think of the most general SPT state as a soup of domain walls that intersect at various codimensions, and where you're enriching those intersections with these SPTs with no symmetry. Okay?
I had a question. So in 2+1D, there's an invertible bosonic SPT phase that goes by the name of the E8 phase.
Yes.
What does that? Where does that feature in this table?
Well, so that's true for a bosonic system. I'm talking about the fermionic system.
But I would assume that if you stack the bosonic system with trivial fermions, that would become a fermionic system. So shouldn't that also appear here?
But that bosonic system can be easily obtained by stacking these P plus IP.
So it's part of the P plus IP, the Z in P plus IP. Is that what you're saying?
Well, I mean, so the A01 is just a system that has central charge 8, right?
With the Cartan matrix.
It's a purely gravitational counter term, and that certainly can be generated by a collection of these P plus IP superconductors.
I see. Okay, thank you.
But the point is, an important point is that precisely. So now you could say what? Okay, so now I'll make a small presentation. You could say what is the analog of that for a bosonic system? And the point is that for a bosonic system, this SPT layer is not there. This SPT layer is not there. But here there is an SPT layer, which is precisely what you said. And therefore, the cobordism group, there's a particular lower dimensional cobordism group that contributes into the computation, which is precisely coming from the A8 level 1 layer, precisely. The fermionic system is much richer because essentially you have non-trivial SPTs at all these lower dimensions in 2+1, 1+1, and 0. So now the idea is that we have this soup of domain walls, and at various intersections we can add at the junctions these guys, okay? And this define these various cohomology classes, okay, that come from the various layers, depending on the codimension of the intersection. Okay? Now, what is the role of these lower dimensional layers? Remember that I said before that for a discrete symmetry, the way you impose like the wedge condition is that you have a network of defects and you make a gauge transformation and then they reconnect, okay? Now you have to do the same thing, but with a network of defects have junctions of at lower degree. And now the usual pentagon identities that we had get modified from the lower dimensional things that live at the intersections, these guys, to modify the pentagon identities, okay? And that's precisely what changes the answer from the group cohomology to the spin cobordism group, okay? Roughly speaking. Good. So here I was going to give you an explicit example of how this works, but given the time, I think I will pass it. But essentially, this was a very simple example of how the existence of an SPT phase in 1 dimension and 0 plus 1 dimension and 1 plus 1 dimensions changes the pentagon identity to something non-trivial, which describes the data of the spin cobordism group. But in words, essentially what I'm saying is that the existence of these lower dimensional degrees changes the associativity relations and build for you the cobordism group.
Excuse me.
So these were very nice, but
there seems to be a question in the chat.
Oh, I can try to read it, but
I can read it out for you. Like,
yeah, I will come back. I will come to this question in this slide.
Okay.
So how do we detect anomalies? Because as a physicist, we care about, it's nice to know the classification, but we want to know whether a physical system has an anomaly or not. So how do we detect anomalies? Now, this is of course well understood for symmetries that are connected to the identity. So that in particular means for continuous symmetries. Sometimes the language perturbative anomalies is used for that, even though I don't like it, but whatever. Usually these anomalies can be detected in many ways, but in particular they can be detected as contact terms in correlators using Feynman diagrams. Okay. Now you could ask, which I think is related to the question is, how are the usual anomalies that you find in textbooks detected in this cobordism classification? And the answer is this: they're captured by the free part of this particular cobordism group. Okay. So let me say more about perturbative anomalies, and let's describe global anomalies, which is really the much more subtle and more interesting case that has come to the forefront in 2 years. So for global anomalies, this includes in particular all anomalies associated to discrete symmetries, and in particular also the Witten anomaly, the AND gates Witten anomaly, the famous SG2 anomaly in 3-1 dimensions. So in principle, there is an abstract definition of how you would detect them. You couple your G-twisted the spin structure, and then you check how the partition function changes under that. Okay, but this is extremely difficult to do. In general, in particular, for example, we do not know how to couple, for example, a spin QFT to an unoriented manifold. So even you don't even know really how to get off the ground and proceed with the analysis. And even when you can proceed with the analysis and when an anomaly can be found, in terms of a rather complicated data like the 8 invariant in systems of fermions, or in terms of F symbols and non-trivial data of a TQFT. So the message is that in general, it's even hard to set up the problem of how you would compute from first principles the anomaly, the global anomaly in a system. And when you can, it's written in terms of rather esoteric mathematical objects like eta invariant. So what I want to describe here in this talk is an elementary method to detect global anomalies, a method that you could be able to use after you finish your first quantum field theory course. And I will do the most simple possible thing, which is always the first thing you should always try, is that we will see that, and surprisingly, this captures a large class of anomalies, is that we will try to detect anomalies by studying the Hilbert space of your theory on a special manifold, which is just a flat torus. So we're going to study the theory on a flat torus and somehow try to understand if the anomalies, if the global anomalies of your system are imprinted in the Hilbert space of your theory. And indeed, what we'll find is that the various cohomology layers that I described before that enter in the classification problem leave distinct anomalous behavior in the way that symmetries are realized in the Hilbert space. So each layer in the anomaly classification will leave a certain signature on the Hilbert space that will tell us where the anomaly is coming from. And what we'll find is that the severity of the anomaly in the Hilbert space decreases with increasing cohomology degree. And sometimes some anomalies are very like they smack you in the face and lead to kind of very severe violations of our usual notions of symmetry, while others are more benign. And how benign they are depends on from which layer they come from. Good. Since I'm running a bit low on time, let me just tell you, in case I don't really have time to describe it in detail, let me tell you some interesting applications of viewing anomalies from this point of view. Okay? As I said before, practically any symmetry in a fermionic system has to commute with -1 to the f. But we will find is that certain anomalies for certain symmetries are imprinted in the Hilbert space of your theory by making the symmetry anti-commute with -1 to the f in the Hilbert space. Of course, it commutes with -1 to the f when it acts on operators, but it will anti-commute with -1 to the f on the Hilbert space. And this has an immediate consequence for the behavior of strongly coupled gauge theories that have this anomaly. In particular, it tells you that the quantum field theories that have this particular anomaly, where G becomes fermion odd, must have a supersymmetric spectrum of states. This is a non-trivial statement about the spectrum of the theory because the spectrum, I mean, the theory is strongly coupled. How would you even compute the spectrum? Notice that this is a non-trivial fact, which is a consequence of an anomaly of a bosonic symmetry, not of supersymmetry. Okay? And the thing that's nice, and I don't know how much time I'll be able to describe it with, is that in some particular cases, we're actually able to test this lemma. Namely, the examples where, of course, we don't have a proof that the infrared dynamics of a strongly coupled theory is what we propose the answer is. But if you believe that the answer that we gave, and you do a computation of the spectrum of the infrared dynamics, you indeed find non-trivially that the spectrum is supersymmetric as predicted by this anomaly argument. So these are kind of an interesting application of anomalies that in certain situations, when the anomaly comes from a particular layer, it predicts that the system has a supersymmetric spectrum.
Sorry, may I ask a question, please? This
Yes.
is true for certain global anomaly or every global anomaly
No,
at this point?
I will come back. So as I will describe, will hopefully describe in the next few minutes, different anomalies are detected in the Hilbert space in different ways. Okay, and certain types of anomalies are imprinted in the Hilbert space by precisely making G fermion odd. So all those anomalies that make G fermion odd will have this property.
Okay, thank you.
There are anomalies that do not have that property, and therefore they do not imply supersymmetric spectrum. But when this happens, then yes. And I will give examples where this happens. It's quite common. It's quite common for symmetries to become fermion odd quantum mechanically due to the anomaly. Did I more or less answer your question, or?
Yes, thank you.
Okay. I think maybe I will, given the time, I will skip this, or maybe not. Maybe I'll skip maybe something else. Here I wanted to give an intuition of why this procedure of computing the Hilbert space on the torus allows you to detect anomalies. And actually, the intuition is extremely simple. I already said that the anomaly, practically speaking, is represented by a class in this fancy cobordism group. Okay? Now, imagine I put the system on a special torus. Okay. Now what I can do is take this class, roughly speaking, and integrate it over a special torus. Okay. So it's like taking an anomaly polynomial in kind of loose languages and integrating it over a special manifold. This gives rise to an effective reduced class, which can be thought of as the effective anomaly class for a quantum mechanical theory in 0+1 dimensions. Okay. Good. So essentially, what we're doing is reducing the anomaly in higher dimensions to the anomaly in some effective quantum mechanics. Okay. it turns out that for this class to be non-zero, so it could happen, of course, that when I do this integration, that the class that I get here is trivial. That means that then that anomaly cannot be detected by this mechanism. But by thinking more carefully about this, you can predict beforehand where do you have a chance for this anomaly to be non-zero. And using simple differential geometry, essentially the place where you will need to look to detect, where you have a chance of detecting anomalies using this method, is by studying the Hilbert space of your theory with non-bounding spin structures on the torus. Namely, these are structures that cannot be extended to one manifold dimension higher. If it could be the bounding structures, which are the ones that can be extended to one dimension, to a manifold one dimension higher, then the anomaly will trivially vanish just by trivial reasons, because if I can extend to one dimension higher, okay, if I can extend to one dimension higher, essentially it means that, sorry, the boundary of the one dimensional higher manifold is the torus, d minus 1. And then I can write this as d of alpha using whatever the Stokes theorem. But this vanishes because alpha is a cohomology, class, essentially. So probably the only place where we have a chance of detecting anomalies is by studying the Hilbert space, either with non-bounding space structure or with non-trivial holonomies for the global symmetry. So that, again, if you have a non-trivial holonomy, you cannot extend it to one dimension higher. Okay? And the thing that's very surprising, and this certainly surprised us, is that this very elementary kind of choice of manifold and is able to detect a very large, surprisingly large number of anomalies. Even anomalies for systems that have time reversal symmetry, where the official way of detecting anomalies for time reversal symmetries is by studying the system on unoriented manifolds. And the point is that we can detect those anomalies by studying the Hilbert space of the theory on a torus, which is obviously an oriented manifold. Okay. So let me start with essentially a very elementary example that you will, where this can be made extremely concrete. This example is kind of too simple but it will flesh out what happens in the more interesting cases that I guess I will not really have time to discuss. So now let's describe what's called the Kitaev chain. Essentially, let's study time reversal anomalies in 0+1 dimensions. Okay. Now, anomalies for time reversal symmetry in 0+1 dimensions arise from 3 layers. There is the bosonic layer that comes from H2, the psi layer, which is the SPT phase in 0+1 dimension, and from the ARF layer, which is the SPT phase with no symmetries in 0+2 dimension. As I already described before, the anomaly here is this Z2 compiled to give you a Z8, okay, anomaly, which corresponds to this binary expansion of nu as an integer, mod 8, okay? So the ARF layer essentially corresponds to nu odd, the psi layer corresponds to 2 mod 4, and the bosonic layer to 4 mod 8, okay? Now, let's find a system where we can study anomalies. And a very simple system to do it is just to study the Hilbert space of a system of nu fermions. Okay, so this is just a trivial system of fermionic quantum mechanics. Okay, just a bunch of nu fermions, and then the symmetries of the system, which include time reversal and Z2F, are represented on the operators in the usual way. Okay, something that's known from work from Kitaev and others is that you can write down a quartic interaction between these Majorana fermions that involve 8 fermions that gaps them out completely, okay? So that means that a collection of 8 fermions has no anomaly because I can gap them while preserving the symmetry. So that tells you immediately that a physical way of knowing as like a poor man's physicist that the anomalies nu takes values in Z8. Because if I had 8 fermions, I can remove them while by gapping them out while preserving the symmetry. And this matches, of course, the fancy cobordism classification. Okay? Now, how are the anomalies for time reversal symmetry realized in the Hilbert space? So let me tell you what the answer is. Now, and we'll see that the severity of the anomaly will increase from increasing the degree of the layer. When nu is odd, the anomaly is very severe. Essentially, there doesn't exist a graded Hilbert space at all. Okay, there is no operator in your Hilbert space that anticommutes with the fermions. Okay? It just doesn't exist. So the basic premise that you have a Fermionic system is already problematic. You do not have a graded Hilbert space. -1 to the f. There is no operator that anti-commutes with all the fermions in the Hilbert space. When nu equals 2 mod odd, we succeed in having a graded Hilbert space, but now the thing that was asked just a moment ago happens. The time reversal symmetry all of a sudden becomes fermion parity odd. So T, which was classically commuting with -1 to the f, becomes anti-commuting. Okay? So for nu equals 2 mod 8, T becomes an anti-commuting, fermion odd operation on the Hilbert space. And then the final layer, the bosonic layer, you have a graded Hilbert space. T is fermion parity even, like you would naively think, but now T, the algebra of time reversal, is realized projectively on the Hilbert space, and T squared equals -1 on the Hilbert space. So we see that in one layer there is no graded Hilbert space. In the other one, the symmetry becomes fermion odd, and in the last one, just a benign thing that the symmetry is realized projectively. Okay. And this is a very simple thing to prove. Essentially, you just quantizing the system is completely straightforward. It's just looking at, essentially, this follows from analyzing the properties of Clifford algebras. Yeah. So I don't know if I have. Maybe let me just make a structure. So canonical quantization of the system tells you that you have a rank nu Clifford algebra of standard form. And then you can use another mathematical fact that the both periodicity of Clifford algebras is a mod 8 periodicity. So these are already kind of mimics what we expected from anomalies, that the properties of anomalies are mod 8 properties. So anomalies have a mod 8 structure. And that matches precisely with the what periodicity of Clifford algebras, mod 8. So let me just give you one particular example, and then I'll probably move on. So let's consider the case of nu odd. Let me just say more concretely what I mean by this. So for nu odd, there is no operator -1 to the f that anti-commutes with the fermions. And that's just a trivial fact that follows from odd-dimensional Clifford algebra. So that means that there is no graded Hilbert space. Another way of saying that there is something odd, strange, for you have an odd number of fermions, is that if you look at the partition function on the Navier-Schwarz sector, so you put the system on a circle, and you put antiperiodic boundary conditions on the circle, you find that the partition function of the system is nu to the nu halves. And notice that this is not an integer when nu is odd. This is another way of saying that this theory does not have a canonical Hilbert space interpretation. There is no usual notion of an integer number of states in the Hilbert space. Okay? And that's just a manifestation of the Tooth anomaly. And now for nu even, just playing games with the Clifford algebra, constructing explicitly the spinor representation using creation and annihilation operators, and using the important fact that T acts on the vacuum, Clifford vacuum, as a particle of overall symmetry. So if you act on the empty vacuum, the one that is killed by all the annihilation operators, T gives you the fully filled vacuum. You can deduce trivially what I stated before, that T will anti-commute with -1 to the f for nu equals 2 mod 8, 2 mod 4, and T squared will be -1 for nu equals 4 mod 8. Good. Given the time, I was going to give you another more non-trivial example in higher dimensions, but I don't really have time to. Let me maybe just move to the, and it has all kinds of interesting properties. Here you can detect the anomaly both by studying the theory with anti-periodic boundary conditions, with periodic boundary conditions, so with non-bounding spin structure, but also by studying twisted Hilbert spaces, because now you have a Z2 symmetry. You have a system with a Z2 unitary symmetry. And now you can quantize the system in the presence. So you put the system on a circle, and now you can quantize the system with a non-trivial Z2 connection on that circle. This defines in some language what is called the twisted Hilbert space. The twisted Hilbert space, again, is able to detect the anomalies by one of these properties, either the Hilbert space not being graded, or the Hilbert space, the symmetry becoming anti-commuting, or the symmetry being projected. but I don't really have time to go to this. If you want, you can look at the slide. I don't know if I can send the slides if people want. They want to see the details. Now let me just discuss the last example, which is very interesting, and it's related to topological superconductors. So here the example is 2 plus 1 dimensional quantum field theories that have a time reversal symmetry of chi squared minus 1 to the f. There is a Z16 classification. Now, the thing that's very interesting about this case is that, unlike the other examples in which I just gave you examples of fermions, essentially, one thing I didn't say is that in both in the examples in 0 plus 1 and 1 plus 1, whenever, I already told you that there are scenarios where nu was, say, 2 mod 4, that the symmetry under consideration became fermion odd. And for those examples, again, you can prove this little lemma that the spectrum of the theory had to be supersymmetric. Okay, and this is interestingly so. And I mean, this was also discussed by Mithat for a joint QCD in 1 plus 1 dimension. But essentially, the statement is that any theory that has an anomaly that comes from that particular layer will have this property in 0 plus 1 or 1 plus 1 dimension, and also, as I'll discuss now, in the kind of more intriguing place of 2 plus 1 dimension. One thing that's special about 2 plus 1 dimension is that it's easy to write down, well, it's in quotes, to write down systems that have this symmetry and this anomaly using fermions, but also non-trivial QFTs. So 2 plus 1 dimension is how the
sorry. Sorry, I understand that you're you know, like you're out of time, but which is the particular symmetry that that shows that, which is the particular anomaly that results in there being a supersymmetry? I did not get that statement.
Yeah, so remember here I said that if I have any system, okay, so I think I read it here somewhere. Yeah, let me. Yeah, okay, so this is the lemma. I read it here. So let me tell you what the lemma is. Actually, it's a more general lemma. Is that any system that is V2 symmetric, it doesn't have to, it doesn't need to be free fermions. You could add scalars, and you cover couplings that project time reversal symmetry. The statement is that whenever the anomaly, which is essentially the number of fermions in the deep ultraviolet, is 2 mod 4, the spectrum will be supersymmetric. So you have a Z8 classification of an anomaly, right? So when the anomaly is always of the type 2 mod 4, then the system will have a supersymmetric spectrum.
Thank you.
Because if nu is not 2 mod 4, then whatever T in this case is not fermion odd. And therefore you have no statement about the supersymmetry. And in fact, it's not supersymmetric. I mean, if you look at the actual examples that we think we know what the answer is, the spectrum is not supersymmetric. Okay, so if we're in 2 plus 1 dimensions, we can study systems and their anomalies, both in systems of fermions and in topological quantum field theories. And the way we do it is again by studying the Hilbert space of the theory, both for fermionic and TQFTs. So actually, in order to solve this problem, we have to go quite deeply into the construction of what is called the spin TQFTs. So these are topological quantum field theories that depend on the spin structure. And one has to learn how to construct the Hilbert space of those theories. Describing that would be a talk in itself, but the point for this discussion is that by studying the torus Hilbert space of the fermions and topological field theories on the now you have 4 sectors, because you can choose either maybe Schwarz or Ramon boundary conditions on the 2 circles of the torus. We find that when nu is odd, so when the anomaly is odd, in the case of free fermions, nu would be the number of fermions. T becomes fermion parity odd in the Ramon sector and is even otherwise. And this is summarized by this neat formula in this way. And when nu equals 2 mod 4, both in the case of fermions and in the case of spin TQFTs that have that anomaly, T square is realized projectively in the Ramon sector. So T square equals minus 1 to the F for all other sectors except for the Ramon sector, where you get an extra sign. So you see that the anomaly, again, is imprinted in some rather elementary fashion in the Hilbert space of the theory. So here I have some story about how to construct, like a quick story, how to construct the Hilbert space of spin TQFTs. I will not have time to discuss. Let me just conclude with a neat example of precisely this supersymmetry. Yeah, I was going to discuss that perhaps surprisingly, So here I was talking about the example of time reversal symmetry, but it turns out that you can write down, perhaps surprisingly, time reversal symmetric Chern-Simons theories in 2+1 dimensions. And those theories can have a time reversal anomaly that we studied by essentially studying the Hilbert space of the theory. So let me just conclude with some lemma that will show you the power of this that a system having a particular type of anomaly can have. So the lemma essentially is that any t squared minus 1 to the f symmetric quantum field theory, it can be a gauge theory, it can be whatever you want, which of course are strongly coupled in 2+1 dimensions, where nu is odd, where the anomaly is where the anomaly with an integer nu and that integer is odd, must have a supersymmetric spectrum. Okay? Now, of course, you would say, okay, this is very nice to say, but how are you ever going to check this? You need to solve for the dynamics of a 2+1 dimensional gauge theory, which is not a really hard thing to do. Okay? But in recent years, the infrared dynamics of gauge theories in 2+1 dimensions has been put forward conjecturally, and they exhibit interesting novel quantum phases, namely phases with emergent gauge fields and emergent anions. So let me give you a particular example that will satisfy these properties, and we'll be able to actually test both the proposal and the statement that the system has a supersymmetric spectrum. So consider SON QTD with a quark in the symmetric representation. Okay? Now, it was conjectured here by complicated long song and dance that in the deep infrared, the system has emergent gauge fields and is described by this particular Chern-Simons theory. So SON plus 2 over 2 at level with the same level, Chern-Simons theory. The first non-trivial statement is that this theory is time reversal symmetric, and non-trivially, this theory is also time reversal symmetric, even though you're taught in school that Chern-Simons terms are not time reversal symmetric. But this is time reversal symmetric by virtue of a duality that maps the theory with negative level to the theory of positive level via duality transformation. Now, this system is time reversal symmetric when n is even. Okay, you just have to count the number of fermions that live here. Okay, and the anomaly is odd, which is the number of fermions when n equals 0 mod 4. Okay? You just have to count the number of fermions, and the number of fermions is odd when n equals 0 mod 4. So the lemma I just described here will tell you that the spectrum of this theory has to be supersymmetric for n equals 0 mod 4. Okay. Now we can try to test this. Okay, because here we stuck our neck out and said, okay, well, this theory in the deep infrared is described by this Chern-Simons theory. This is a twin Chern-Simons theory. Okay. So now what we did with Diego is compute the Hilbert space of the theory on the two torus of this particular Chern-Simons theory. So we generalize it to SON with odd rank and odd level. And now, okay, so this is a complicated story that I didn't get into. You have to understand how to construct the Hilbert space of spin QFTs, but doing that work, you can compute the number of bosonic states in the torus and the number of fermionic states in the torus, and you see that they are not the same. But lo and behold, whenever you plug in this value here and n equals 0 mod 4, you indeed find that the spectrum is supersymmetric. So this non-trivial prediction that the spectrum had to be supersymmetric is realized by this conjecture answer for the infrared dynamics of this particular gauge theory. Okay, so I'm completely out of time, so I'll just stop here and leave this slide here if you want to read it. Thank you very much.
Thank you for that wonderful talk. So if people have questions, you can ask the speaker.
So may I ask a few questions regarding this? So what about Witten SU2 anomaly in 3+1 dimension?
Beautiful question.
Can
yeah.
you
if I can
say something about?
Right, I can say something.
Yeah.
I can say something. Which actually, I cannot detect it by studying the torus Hilbert space, but I can detect it in a very elementary fashion by using the kind of a little bit the spirit of what I discussed here. So let me go to this dimensional reduction picture here. Okay, let me erase this. Okay. So Witten anomaly is an anomaly that happens can happen in systems in 3+1 dimensions that have an SU2 symmetry. Okay. Now, it's known, so it's classified by a certain cobordism group in 5 dimensions, which actually happens to be a Z2, okay? Now, you can write down very concretely, you can write down very concretely what this cobordism group is, cobordism class is. So the analog of the anomaly polynomial for this class. Okay, and it's written, in, let me write it, let me call it alpha, I guess. I call it alpha 5. Is something that you learn in field theory courses. So it would be the second shared class of the SG2 bundle. So you have a SG2 connection. You're trying to study an SG2 anomalies. You have a Z2 class. So this is like the instanton number, right? And then wedge eta, where eta is the SPT. I described this earlier. The SPT class is not symmetric in 0+1 dimensions. Okay. Actually, this is the guy that precisely. I'm in the wrong place. I don't remember where I discussed. It's actually, this comes from here. Okay. This eta is precisely the topological class that describes this SPT phase. Okay. So the first statement to make is that, and that's not something that Witten did, but you can do. You can write down what the SPT class describing the Witten anomaly is this thing. Now, how would you detect it? You can try to use the same logic as I use here. I want to find some manifold or some background field configuration that will detect the anomaly. Okay. Now, of course, since this guy is involves the instanton number, the obvious thing to do to detect it is actually extremely simple. And by the way, and this picture also tells you, it will tell you where the Witten anomaly arises from this layer construction. Okay. It will tell you that it arises precisely from this psi layer. So the way you can try to detect this anomaly is that you study the theory on an S4, and you turn on a background with instanton number 1. Okay, so that when I integrate alpha 5 over this background, I just get eta. Okay, which is an SPT class in 0+1. And now this tells you immediately an extremely elementary way of detecting the anomaly that does not rely on eta invariance or anything of this sort. All that you have to do is the following. You study your system in a background for an SG2 connection with the instanton number 1. Now, and by the way, and this tells you that since the answer is eta, this tells you that this is associated with an anomaly for -1 to the f. Because remember that I said that these SPT classes that eta comes precisely from SPT classes with no symmetries. The only symmetry is -1 to the f. Now, how do I make this? How do I reconcile this with physical language? Well, one way to reconcile it is that now I study my system in this instanton background, and then essentially you have a 1 fermion 0 mode. So if you study the Dirac equation in an instanton background, you will have exactly 1 fermionic 0 mode. So that tells you that in order to have a non-zero correlation function, I have to study essentially this. And this will be non-zero, right? In order to soak up the 0 mode, I have to insert explicitly a fermion into my path integral. But now notice, what is this? This is exactly a violation or an anomaly for the -1 to the f word identity. Because the word identity will tell you that this correlator should vanish, but now this changes sign. Okay, so the Witten anomaly is detected by virtue of the fact that if I put the theory in the first sphere with instanton number 1, the -1 to the f word identities are violated. Did I answer your question?
Yes, exactly. Yeah, thank you.
I had a question. Sorry. So when the spectrum is supersymmetric, it's easy to construct supercharges and show that the Hamiltonian is a supersymmetric quantum mechanical system. We do that explicitly with Juan Wang.
No. Sorry, what's your point?
I was just wondering whether this observation is completely inconsequential, or does it say anything interesting about the dynamics?
Well, it tells you something non-trivial. I mean, if I give you the spectrum of QCD and you discover that supersymmetric in the infrared, that would be a non-trivial consequences. But this is not supersymmetry. I mean, it's both Fermi degeneracy, but it's not. There is no supercharge. There is so it's not supersymmetry in the usual sense where you have a supercharge associated to it.
No, I mean
there is no local supercharge. Let's put it that way.
Right. Okay. I agree, because it's easy to prove that whenever there's a Bose-Fermi degeneracy, you can explicitly construct supercharges for an n equal to 2 supersymmetric quantum mechanical system that's spontaneously broken.
But here, for example, notice that it's very, very important that I only have. So let's see. So are you saying that you know how to construct a supercharge? If I take this theory I was describing here. I'm telling you that it's in the Ramon sector, there is a supersymmetric spectrum. Are you saying that there is a supercharge that will relate correlation functions in this theory? I think the answer is no. You seem to say that.
There's a constructive proof. Like I wrote a paper with Zhou and Wang where we show this for 0 plus 1D, and the same arguments go for any dimension. Dimensionality is sort of irrelevant. So you can just construct operators that are off diagonal in fermion parity and then show that explicitly that they are they commute to the Hamiltonian, generate the Hamiltonian, n equal to 2 supersymmetric quantum mechanical system. But they're not local. That you're right.
Yeah, no. Yeah, so that's why I use the word local. Yeah, so here it's very important somehow that I need to know about kind of the global property around the circle, right? It's very important that this only happens if I have a Ramon sector. So yeah, so in a very definite sense, I think there is a certain sense in which you can write some non-local supercharge, but not a local one. Right. I would be interested if you send it to me. That I don't know this paper you're referring to. I would like to have a look.
Yeah, actually, you reference to it, like with Zhou and Wang. You reference to it in your talk.
Oh, yeah. Okay. So this was in 0 plus 1 dimensions then.
Yeah, 0 plus 1. That's right. Yeah.
Okay, good.
I actually had another question.
Yeah.
So there's this paper by Vishwanath and Grover where for the boundary of a 3 plus 1D topological superconductor, they show that the critical theory on the boundary of a 3 plus 1D topological superconductor has space-time supersymmetry.
I found that that was not. I mean, I'm not familiar with this result, but I would be very skeptical if no is not too much for. Because
so can you repeat that?
No, I'm saying that this lemma. So when you mean supersymmetry, you mean what more precisely?
So they demonstrate that the critical theory on the boundary of a 3 plus 1D topological superconductor and 3 plus 1D topological insulator between certain phases.
When you mean topological superconductors have a Z16 classification, right?
Yeah.
So you're saying that for any value of the anomaly that
no, for a specific one.
Oh, so maybe it's for exactly these values I'm discussing here. Whatever, odd nu.
Right. So your entire talk was based on phases of systems where the global symmetries have anomalies. So the natural question is whether there are many examples which all of which are consistent with what you just said. So my question is, would it be plausible to say that the critical theories, the anomaly matching only happens if the theory has space-time supersymmetry?
Again, spatial supersymmetry in this more relaxed sense. Because as we discussed, I mean, there is supersymmetry, there is a supercharge, but it's not local in the usual sense. So I don't know, when they say supersymmetry, I don't know if they mean honest to God supersymmetry, the standard one,
yes,
or they mean this more non-local one.
No. They mean like space-time supersymmetry with the local action and things
like that. I am skeptical of this result, but so it says Vishwanath and who?
I'll send it to you, Vishwanath and Grover.
Okay, please send me the email. Yeah, I want to look. Yeah, thank you for the comment. They're looking at gapless boundaries.
They look at the simplest example is the topological insulator, where they go from the Dirac cone to some kind of a symmetry broken phase on the boundary, and the critical theory there is has space-time supersymmetry. Okay,
but I mean, of course, the classification of topological insulator, I have not really thought about whether, I don't even remember what the anomaly classification in 3+1D for topological insulators is, but whether for any of the for any anomaly the symmetry becomes Grassmann Fermion odd. But you seem to say that for some values it becomes Fermion odd.
That's right. Yeah.
Okay, I'll have a look. Thank you.
So Loga had a question.
Yeah. Hello. Yeah. So I just wanted to kind of understand the statement that. So the statement is that the spectrum has a Bose-Fermi degeneracy, but there is no like super current. There may be a supercharge, but there's no super current. Is that the statement?
Yes. There is no local supercurrent.
There's no local supercurrent.
But still, it's still an obvious statement that you have a Bose-Fermi degeneracy given a gauge theory. Yeah.
Yeah. Maybe I'm just generally puzzled by this statement. So this would be kind of somewhat counterintuitive from traditional some naturalness kind of things, right? I mean,
which kind of thing?
Naturalness kind of arguments. Like if I just find some theory which
it's protected by an anomaly. So
okay.
It's protected.
But okay, you're saying that like for example.
So maybe we're not clear with this. I mean, that's why I think this is interesting. Both Fermi degeneracy is protected by a supersymmetry usually, right?
Yes.
Now the point I'm making here is that this is an example in which Bose Fermi degeneracy is protected by an anomalous bosonic symmetry.
Okay. Like
like time reversal.
But you're saying the Hamiltonian, like for example, how does it work at the level of dynamics? I mean, this doesn't have hierarchy problem or something. I mean,
no. I mean, of course, it's less powerful because there are less bells and whistles attached to it. It's less powerful than a conventional local supersymmetry, but so it does not have the same consequences like holomorphy or whatever of standard supersymmetric theories, but it has the power to tell you about the spectrum. Essentially, it's derived essentially from a consequence of how the symmetries are implemented on the Hilbert space of the theory. It's only able to tell you something about the spectrum on the Hilbert space. I don't think the supersymmetry will lead to the constraints that the standard supersymmetry, linearly realized supersymmetry would give you. There is no reason for it to do that.
Can I make a remark?
Of course, yeah.
So, for example, in 2 dimension, what's happening? Let me just give you an example. There is a mixed anomaly between the 2 discrete chiral symmetry and, as Jaume mentioned, -1 to the f fermion number modulo 2. So that tells you that if you calculate, for example, partition function with periodic boundary condition on the torus, it is exactly 0. Okay, so there is level by level cancellation. However, how this is happening is that the full Hilbert space, you have to better think of it as some generalization of the superselection sectors. There is a bosonic vacuum on top of which you can construct a Hilbert space. There is a fermionic vacuum on top of which you can construct a Hilbert space. There is no local operator, on the other hand, even in finite volume, that can connect these 2 things. So there is an exact degeneracy, but as Jaume said, it is precisely dictated by the mixed anomaly. And these 2 sectors are like generalization of the superselection sectors, sometimes called universes.
But Micha, I mean, this example you're discussing, I mean, is that special to being in 1+1 dimensions?
Maybe there may be something special to 1+1, but
this universe's business is very special. It seems to be very special to 1+1 dimensions.
Yeah. For the universes, you have to have some mixed anomaly between D-1 and D-1 form symmetry must get involved. In that regard, yeah.
The point, 1+1 dimensions, it just happens that the one form symmetry is implemented by a local operator. So that kind of clustering implies universe.
Right.
Even in higher dimensions, I don't have an argument like that.
Right. That's correct. Yeah.
So I think.
I mean, let me just rephrase the question. Maybe can one write down a like some kind of a Lagrangian which is not supersymmetric? Like, is there an explicit Lagrangian that you can write down which is not supersymmetric, but which which by this argument has supersymmetry?
Yeah.
Yes, of course. Yeah.
Okay, we discussed SON Young Mills with a quark in the symmetrical. That's an example.
Yeah. Sorry. I was thinking of say. Do you have a 3+1D example?
No,
this was in 2+1D, right?
No, I would love to have an example in 3+1D, but I don't. But if you really ask me, I am convinced that there are examples in 3+1D that have an anomaly where the generator becomes Grassmann fermion odd, and therefore there will be a supersymmetric spectrum. I just have not really nailed it yet.
Yeah.
Have you thought about it? Have you thought about that?
There is a very funny thing. Okay, if you let me to mention, it is not really related to anomaly between -1 to the f and something, but if you take QCD adjoint on 4 dimension, it has the following super weird property. Okay, if you look to twisted partition function, graded partition function with -1 to the f insertion, and consider this theory on S3 times S1. Okay, like Zohar and his friends showed that for supersymmetric theories, the sign density of states, relative density of states, exhibits a two-dimensional behavior, on S3 cross S1. QCD adjoint, okay, on S3 times S1, in the large N limit, also exhibits two-dimensional growth of the relative density of states. In that sense, there is an immense conspiracy taking place within a Hilbert space. But this is not in the spirit you described, however.
But this is, I mean, the examples I was discussing, these are examples finite n. The statement about the spectrum being only a large n.
Right. Exactly.
I can believe it more because at large n, essentially, the glue balls, whatever, they all become free. And I believe that, in free systems, it's easy to have many symmetries. I mean, it's a very interesting example, but I think really the physics behind it is quite different than the physics that.
Yeah. This is the reason it is not in the. I do not know an example in the sense that you have given the example in 2+1 or 1+1 or I do not know such a.
But I know there are symmetries in 3+1D. So the examples of 3+1D that have large Stuft anomalies, which potentially could have. And a simple example is if you take a symmetry where a Z2 symmetry where G squares to -1 to the f. That guy has actually a Z16 anomaly. And in principle, there could be such supersymmetry in systems that have the right anomaly in set Z16 that would have a supersymmetric spectrum. But I haven't really been able to really prove it.
I see.
But you need to use this spin C structure idea where fermion number is entangled with your symmetry. It's not a direct product.
Right. By the way, I had a question. Could you tell some things about this spin TQFT? You skipped over quickly, if you don't mind.
I can, yeah. If I'm able to go back to. Pick me out always from. No, so now I have to go back to. I'm in Zoom. Oh, no.
It's okay if you can't access it. It's okay.
I can tell. I mean, it's a long story, but I can tell you like a highlight.
Yeah, highlight would be good enough.
Yeah. Sorry. I'm not good at this stuff at all. Okay. Okay, so here. Okay, so yeah, so the first comment to make is that even though usually topological quantum field theories are not necessarily described in terms of Lagrange and stuff like that, but it's easy to write down examples of TQFTs that depend on the spin structure, okay, and the Hilbert spaces are graded. So, but actually, the way that we have of constructing those spin TQFTs is by the idea of gauging. Okay, so let me start from a thing that you will know, or you will know both, but anyway, so you can always make a bosonic theory out of a fermionic theory by gauging fermion parity, by summing over spin structures, essentially. So imagine I give you a spin TQFT, then I can gauge fermion number, which is the same as summing over spin structures, and to give you a bosonic TQFT. Something that is always the case that is whenever you gauge a symmetry, you get back a bonus symmetry or a dual or a kind of a dual symmetry.
Mm-hmm.
For a very long time, at least in the context of two-dimensional conformal field theory, but it's
very nice.
One way you can construct the spin TQFT is by taking a bosonic TQFT and gauging the dual Z2-1 form. Now, in the language of condensed matter physics, gauging this very special Z2-1 form symmetry. So the Z2-1 form symmetry is generated by an anion that has a half integral spin. Okay? This does not enter the usual rules that people in condensed matter have used to describe anion condensation. They usually condense bosons, not fermions. But it turns out that you can generalize the notion of condensation to fermions to construct a spin TQFT out of a bosonic TQFT. And the message here is that any answer, you don't have to guess anything. Anything you want to know about the spin TQFT can implicitly be obtained by looking deeply enough at the intricate data of the bosonic TQFT. Now, it may happen that to answer some questions, it's not enough to look at the fusion rules and the anion spectrum. You may have to look at more complicated data of the bosonic TQFT, like the F symbols, like the 6J symbols of the spin TQFT. You know, bosonic TQFTs, the data is that of what's called a modular tensor category. So there's elaborate data that people usually ignore, but actually that you need in order to really answer simple questions about the spin TQFT here. So now what you can do is, so for this particular, so let's focus on constructing the Hilbert space of TQFT. Again, since the theory depends on the spin structure, there are 4 Hilbert spaces depending on my choice of boundary conditions. Now there are 2 types. So, let me step back. So in the usual language of TQFT, there's a one-to-one correspondence. Bosonic TQFT. There's a one-to-one correspondence between the Hilbert space of a bosonic TQFT on the torus and the space of conformal blocks of the corresponding chiral algebra on the torus. Okay. And the way, and the way, are you more or less familiar with that, or should I go more into that?
That's okay. That's the right level, more or less. I see.
Yeah. So let me tell you what's new. In the usual bosonic world, you would associate. So the way you construct a state in the Hilbert space of Chern-Simons theory or a spin TQFT is that you look at the solid torus. So you have time, you have the solid torus, the torus, and you insert an anion, a Wilson line, along the A cycle of the torus. Okay, this defines for you a state. Okay, and usually we have this picture where you represent the conformal block judged by the one-dimensional version of it. Now, what are we doing here? We're gauging a one-form symmetry. That means that in the gauge theory, emitting the fermionic particle that we gauge is trivial. Okay. I mean, in the gauge theory, there is no psi particle, right?
Right.
Gone. So here, the novelty that happens here when you do these reductions, and when you study Hilbert space on the torus, you also have to consider the Hilbert space on the torus, but with one puncture being the psi anion that you're condensing.
I see. Okay.
So the spin TQST comes from the usual conformal blocks on the torus, but also from the conformal blocks on the once puncture torus.
Okay, very good. I got it. Okay.
Now, to make a long story short, essentially, the whole complication arises from the fact that you have to consider, to study the states of the spin TQST on the torus, you have to consider the once puncture torus.
I see. Yeah.
So then it's very easy to write down what the Hilbert space on the torus is. Essentially, the main point I want to make is that the interesting thing happens in the Ramon sector. So for the other states, essentially, these are things that you would know how to do. Essentially, since you're gauging, essentially, for any state, for any anion that you have A, you have to add the Z2 symmetric image. So to a state created by A, you have to make a linear combination with the gauged counterpart, where A is to the T. So you find this. So in order to get these signs, you have to look at the modular transformation properties. These are just details. Now, in the Ramon sector, in the Ramon sector, I should say that this theory has a collection of anions, and anions will have a certain charge with respect to the Z2 one-form symmetry. Some of them will be neutral, and this will correspond to the NS lines labeled by A, and some of them will be. And this will be labeled by the lines that I call X and the lines that I call. Now, what is the difference between these two? And that's very important, is that the lines that are fermion odd, they can either appear when fusing with the condensing fermion as in pairs, like a two-dimensional representation, so X times psi, or they can be a fixed point. We call these M Majorana lines. It could happen that there are anions that if you fuse a fermion with it, you get back the same anion. So I mean, with the Hilbert torus come from states that are either in essentially constructing the usual by adding a state with its Z2 partner, or you can create this from a Majorana line that it's a singlet. And why is this consistent? I mean, this state only makes sense if the fusion rules are satisfied. So if M times psi equals M. So the Hilbert space on the torus will have more or less a standard state, but now that you can have these Majorana lines in the Ramon sector, you have states that come from the one puncture torus. And that's exactly where the fermionic states come from. All the states that I've written here, all of these are bosonic.
I see.
But these states that in the Ramon sector that come because you can have Majorana lines and therefore you can create states from the one puncture torus. The fermion odd, these are where the fermions come from.
Very good, very good. I got the point. Yeah, this is the how the fermions appears from the dual side of the story. Yeah.
So this is very clear that you're gauging the fermion, so therefore you should allow fermion lines to go. That's why you have to consider this one-point block.
Okay. Okay, thank you very much. Very good.
So are there any more questions? Okay, if not, let's thank the speaker once again.
Thank you very much. Thank you.
Thanks.
I have some questions about your papers in 2D. I may want to ask you about them. Maybe we can set up a call one day next week, if that works for you.
Of course. The voice broke up for a moment. You asked me, right? Okay.
Yeah. Okay. So I'll send you an email, and maybe we can discuss.
Okay.
Sometime next.
Okay. Sounds great. Okay.
Okay. Thank you very much, everyone. Bye.
Thank you, Jaume. Bye bye.